More on limits of exponential functions. For any real number x, the limit of b raised to x as x approaches a is equal to b raised to a. The limit of b raised to f of x as x approaches a is equal to b raised to f of x as x approaches a. Find the limit at infinity. Exercise 1.22, find the limit at infinity. So we shall evaluate the limit of our exponential functions as x approaches infinity or negative infinity. Find the limit of e to the 2x minus 1 as x approaches infinity. So it is equal to infinity. How about this? The limit of 5 times e to the 2x or 3x minus 27 as x approaches infinity. The limit of a constant as x approaches infinity is the constant. So this is just minus 27. So it is equal to infinity. I am presenting a detailed solution because I am imagining that this is an assignment or this is an exam, the problem-solving part of your exam. And usually teachers would require you to produce a complete and orderly solution. So I would advise you to do this. If that is the instruction, produce a complete and orderly solution. So this one is equal to infinity. Find the limit of e raised to 5 divided by 1 plus x as x approaches negative infinity. So what is e to the 5 divided by negative infinity? So that would have to be 0. Okay, so a constant e to the 5 is a constant real number. That's e multiplied to itself 5 times divided by something that decreases without bound. So the result is going to be 0. Find the limit of 3 times x cubed minus 5 raised to 2x plus 1 as x approaches negative infinity. Now look at this. This is negative infinity. But what about 5 raised to negative infinity? What is that? Is that equal to infinity? negative infinity or to something else. So 5 to the negative infinity, you can write this as 1 over 5 to infinity. And so 1, a constant, divided by 5 to infinity. 5 to infinity is infinity. And so when you divide 1 by that, something that grows in size without bound, that is bound to give you something that is so small, it is practically equal to 0. So this one is equal to negative infinity. So the limit of this function as x approaches negative infinity is negative infinity minus 0, which is equal to negative infinity. How about this? What is the limit of x times e to the x divided by 5 minus x raised to 2 as x approaches 5? So this is equal to limit of x as x approaches 5. That is just 5 times e to the 5. And then divided by something that is approaching 0. So this is a constant divided by something, a quantity that approaches 0. And it is positive because it is raised to 2. Is equal to infinity. So the limit of this function is infinity. Theorem 1.12, the limit of e to the x minus 1 divided by x as x approaches 0 is 1. Okay, so let us get the limit of e to the x minus 1 divided by x as x approaches 0 using what we know about the limit theorems of exponential functions and a simple polynomial function. So this is going to be the limit of e to the x minus 1 as x approaches 0 divided by the limit of x as x approaches 0. So we know this to be e to the 0. The limit of that as x approaches 0 is going to be e to the 0. And then the limit of a constant is just 1. And then our denominator becomes 0. What is e to the 0? E to the 0 is 1 minus 1 and then 0. This is an indeterminate form. It's 0 over 0. It is indeterminate. So what I'm going to do now is I will show you how the limit came to be equal to 1 by producing a table of values. Using our theorem for the existence of limit, we will look for the one-sided limits. What is the limit of this function? What is the limit of e to the x minus 1 divided by x as x approaches 0 from the right? Okay, we will look for that. And then we will also look for the limit of this same function as x approaches 0 from the left. What is that equal to? And this theorem is telling you that these one-sided limits are equal. Okay, so let us produce a table of values for this function. So we can approach 0 from the right. So that means we can begin from 0.1. We get closer to 0, 0.01, and then closer to 0 again, 0.001, until we get here, or even farther than here, closer to 0. And look at the resulting values of our function. It gets close to 1. Now let us approach 0 from the left. So you will start from the negative values of x. We can start from negative 0.1, negative 0.01, so on and so forth. When we get here to this point, to something that is close to 0 from the left, from the negative side, the value of our function approaches 1. It's 0.999972. This tabulation of values is telling us that the one-sided limits are equal. And using our existence theorem, or theorem for the existence of limit, the limit of this function exists and it is equal to 1. Now we can also easily and quickly agree with this result if we are to look at the graph, because this is the graph of the function f of x is equal to e to the x minus 1 divided by x. And look at this. As x approaches 0 from the right, our function approaches that point. As x approaches 0 from the left, our function approaches this same point. And what is the value of our function at that same point? It's equal to 1. This graph, this is the graph of the function we are working on, is also revealing some other things. For example, the limit of e to the x minus 1 divided by x as x approaches infinity is infinity. If we are to apply our limit theorems here, what we will get here is something like infinity, okay, because this one is infinity, divided by infinity. But this one is an indeterminate form. But looking at the graph, as x approaches infinity, our function increases without bound. So it approaches infinity. And another result that we can see from this graph is this. As x approaches negative infinity, look at this. Our function approaches the horizontal asymptote. And that is the line y is equal to 0. And so this is telling us this result. As x approaches negative infinity, the value of e to the x minus 1 divided by x is equal to 0. So remember these results, because we are going to use this to find the limit of functions, of exponential functions, whenever they produce indeterminate forms. We shall return to this when we are solving indeterminate forms that arise from exponential functions.